All right. So I think I'm recording now, and let me go over to my um, screen here. All right. So we're going to talk about something really interesting today, the EPR paradox. Okay, and it's something that formed the founding stone for like quantum information, modern quantum information theory, because it introduced this idea of spooky action at a distance, which I'm sure that you have heard about. Okay, it's also called the non-locality of quantum mechanics. All right. And it all started with this paper by Einstein, Podolsky, and Rosen. And this was in the 1930s. And I will send you the original paper, all right, along with a question. There is a homework question that I have on that paper. Um, all right. And so you'll see it's a remarkable, remarkable paper. It's one of the most cited papers in the history of science. And you'll get a look at that. I want to describe this to you, all right, like what this means. And in order to do that, what I'm going to do is, well, let's see what this actually means. All right. So what we're going to do, and I guess there's a couple things that I'll have to now before I start. If this system knocks me out, like like it did last time, after 30 minutes or 40 minutes or whenever, then I will come back and post another. I'll have to make another video lecture to finish up. All right, well, let's get started. So let's say that you have, for concreteness, in order to show what this means, let's consider the decay. Now, this is not in the book, okay? So you'll have to rely on these class notes to understand the EPR paradox. And also, let me just say what it is. E stands for Einstein, P stands for the second author on the paper, Podolsky, and R stands for Rosen, the third author. Okay? So Einstein's the first author. So that's where the name EPR paradox comes from. And it really makes concrete this idea of this very disconcerting idea. That's why it's a paradox that in quantum mechanics, if quantum mechanics is true, and all experiments to date have shown that it is true, then it implies that you can have this spooky or ghostly type of action at a distance, also called non-locality. Okay. Okay, so let's go over this. Consider the decay of a pi meson, okay? A particle, a type of particle, pi meson. It's also given this sort of designation, pi naught. And pi naught comes from because it has spin zero. So there are some facts that I'm just going to state, and you have to. These are well-known facts. Just accept them that there's a particle pi meson with a spin zero, and we're going to consider the decay of this into two photons of equal energies, okay? Gamma 1 and gamma 2. So basically, you have this pi meson, right? And let's say it just spontaneously decays into a gamma 1. and a gamma 2. All right. And this was your pi meson. And let's set the axes, the axis along which these photons are traveling. Okay, so that's, let's say, z, and then y would be at right angles to that. And to make this a right-handed system, that means x is coming out of the page. All right. And this decay tends to happen over a time scale, like it happens pretty fast. So these two photons are emitted out like within, a time scale of 10 to the minus 16 seconds. These are experimentally observed facts. Okay, and so what's known here is that pi meson has spin 0, and the photons, gamma 1 and gamma 2, have spin 1. Okay. Spin 1 meaning that the photons that, you could think of the photons having spin, right? So if now this is a very pictorial sort of hand wavy way of saying it, but here's a photon and it can be spinning like this or it can be spinning like that, right? So spin 1, either +1 or -1, okay? And what we know this as, we call this right circularly polarized or left circularly polarized. Okay. So now that's something I guess I have to um, sort of remind you of. All right. So this would be like, I mean, let's just say this is right circularly polarized. This one, let's say, is left circularly polarized. There are several things I'm sweeping under the carpet, under the rug, but I'm the abbreviation RCP, LCP. And let me remind you, I guess, how we in ENM electromagnetism we're taught about right and left circularly polarized light. So a quick aside here, okay, and this is a reminder on RCP and LCP. Okay, so what it is that, let's say you have um, x-axis, y-axis, and let's say you have an electric field, like a light wave maybe traveling with its electric field, let's say like this, right? So it's linearly polarized, right? And it has a x component there, and it has a y component there. Okay, and in this case, you would write the electric field vector. Just a reminder from EM class. Okay, so the electric field you can write as E sub x in the direction x plus E sub y in the direction y, right? And something that is important to realize is that in this description and in this picture, what we're not seeing, okay, so we have a E sub x going this way and a E sub y going that way, and the superposition of those vectors gives me the total electric field. But what we're not seeing is that the E sub x may have a phase shift with respect to E sub y. Okay, so how do I express the phase shift between these two components? I stick in a e to the I theta, okay? And what this is saying is that EY, so this is in general, I'm writing out a general description of an electric field vector, and I'll explain what the phase shift means in just a moment. But EY is phase shifted, so phase shifted by some angle theta, right, with respect to E sub x. Okay. And so what that means is that if you have, let's say, this is E sub x, right? And let's say it's oscillating something like that. And this guy here, and let's draw EY here. Okay, so this is pi over 2. This is pi 3 pi over 2, 2 pi, and so on, right? This would be 5 pi over 2. This would be 3 pi. Okay. And so now if that's EX, and let's say I want to depict a shift of pi over 2. Okay. So shift of pi over 2. So I'm drawing this for, so this is a depiction for theta equals pi over 2. All right. So then E sub y is shifted by pi over 2. So that means the crest now has to appear here. Okay, so it would be like this. Right? And you notice that and so, like that. And so you notice that the shift between the crest here, here, it's shifted, right? So I'll use this. So this here, this here, they're shifted by pi over 2. Okay, and so the combined electric field, E, is the sum of these two, vector sum of these x and y components. All right. So anyway, so the point is that in general, that's what your electric field uh, can be written as x and y components. If theta is 0, then they're in phase and you get linearly polarized light. All right. But so actually, let me write that out, that if theta equals 0, right, then you just have linearly polarized light. Linearly polarized light meaning that the electric field vector in this case is pointing as shown in this diagram, and that's the direction in which it points. And so it's linearly polarized at that angle theta. Well, whatever angle this is. I don't want to confuse it with this angle theta, whatever this angle is. So let's say this is, some alpha. Okay, so if theta equals 0, we have linearly polarized light at angle alpha to the x-axis. Okay. Um, on the other hand, the condition for circularly polarized light, okay, so on the other hand, the condition for circularly polarized light, actually there are two conditions. So conditions for circularly polarized light, okay, they are that the two components E sub x and E sub y should be equal in magnitude. Okay, E sub x equals E sub y equals, they're the same thing, let's say E naught. And the other condition, okay, the other condition is that um, the theta that I put into the formula there, theta must be pi over 2, as depicted in the diagram here. Okay, so if I put these two conditions in, then what do I find for circularly polarized light? So now for circularly polarized light, what I find is that the electric field, therefore, would look like, uh, the E sub x and the E sub y are the same. They're E naught, so they're a common factor, pull them out. And inside I have x plus e to the I, now theta is pi over 2, right? Y. And of course, e to the I pi over 2 is just, this guy here. What do you think that is? Well, that's just I. Oops, that's just I, right? Cosine pi over 2 plus I sine pi over 2. So I have E naught x plus IY. Okay. Now so this is referred to as, let's just, without going into too much detail, let's say that this is referred to as right circular polarization. Okay. Um, you could have easily also had a phase shift of minus pi over 2. All right. So that would give me, so this is right circularly polarized with the plus, but on the other hand, if I phase shift of minus pi over 2, if theta is minus pi over 2, then the electric field becomes E naught x plus e to the minus I pi over 2 y, okay? And this is E naught x minus IY. And this is, let's call this left circularly polarized light. Okay, so the idea is that, so this was the reminder, I suppose, that if you have this kind of um, polarization, right? The polarization vector is given by this in the parenthesis here, x plus IY. So then that would correspond to this situation. On the other hand, if you have um, theta equals minus pi over 2, right? So this here was for theta equals plus pi over 2. The theta equals minus pi over 2, where you have with the minus sign in there, okay, that corresponds to this situation. All right. So spin 1 or minus 1, those are the two options here. So that's what the photon is. All right. Now one last thing here. So anyway, let me just finish this discussion. So this was the aside, okay? And to carry on then, what we get from this, well, actually, maybe I'll continue it as an aside for now, because this is still a reminder. So the polarization vector, the polarization vector is, the amplitude is the E naught, and the polarization vector is all of this. Okay, so it's x plus or minus IY, polarization vector for circularly polarized light, right? And so, you want to normalize it. The normalized polarization vector for circularly polarized light is going to be x plus minus IY, and these are unit vectors, right? So uh, the sum, the absolute values, the sum of the absolute value squared of each component, will give you a half. And so you need to normalize it by dividing by 1 over square root 2. Sorry, the sum of this absolute value squareds would have given you a 2, and that's why you have to divide by square root 2 on the amplitude. All right. And so one last thing I guess that we can say about circularly polarized light is that clearly, as you can see from the polarization vector, circularly polarized light has equal amounts of X and Y polarization, right? In it. X and Y polarization in it. What I mean by that is that it's made up of um, is made up of equal of 50%, X and 50% Y. Okay? So if you think of those two photons, gamma 1 and gamma 2, right? This one, gamma 1, gamma 2. So if I look at what's going on with them, so let's say that you have gamma 1 coming out this way, um, and then you have a gamma 2 coming out this way, all right? And let's say that I put on let's put on a circularly polarized, let's say I have a circular polarizer analyzer is what it's called. Let's say I have a circular polarization analyzer, all right? So let's say, let's do it like this, that let's say I put a circular polarizer here, okay? Actually, yeah, okay, that's fine. Circular polarizer here. Let's say I put a right circular polarizer here, right? And a right circular polarizer on this side, okay? And um, can I make this statement right now? No, I can't. I'll have to come back to this. All right, so let's forget I said this. I'm going to, in fact, that was the end of the aside. So let me just erase what I did here. Sorry. So this goes away. All right, and so this ends my aside on circular polarization. Um, yeah, in fact, I'll leave this space here. Because I want to come back to this a bit later. Okay, so touch this space. Right. Okay, so now let's make some we know what circular polarization is. We know what this pi meson is decaying into. It's decaying into these two photons, all right? And it turns out, okay, so now here's some facts that you'll have to accept about the decay, uh, and but they're very reasonable. Like, for example, in the pi meson decay, we expect angular momentum to be conserved. So in the pi naught decay, we expect angular momentum to be conserved. And just remember, I mean, it has the master of logic, Mr. Einstein, involved. So there will be some beautiful, simple logic that will make it clear what the spooky action at a distance is. All right. Um, so you have to just follow it. All right. So in the pi meson decay, we expect angular momentum to be conserved. And what that does for you is that as a direct consequence of this, it turns out that if gamma 1 is right circularly polarized, let's say, okay, so if it is right circularly polarized, then that means so is gamma 2. And on the other hand, if gamma 1 is left circularly polarized, then so is gamma 2. Okay, so that's something that it's reasonable to accept. Okay, and so what it means is that if I want to write down the state, you know, for the two particle system, therefore the quantum state of the two photon system can be written as if, let's say, photon 1, gamma 1 is right circularly polarized, then also gamma 2 is right circularly polarized. So it has to be this, or if gamma 1 is left circularly polarized, then so is gamma 2, right? So L2. And there's no reason to expect that any one of them is more probable than the other. So these are equally probable. And so when you have two states that are equally probable, it means that your quantum mechanical state of the system, okay? So therefore the quantum state, uh, let's call it phi. So now if two states are equally probable, then quantum mechanics tells me that the general state then is a superposition of these two states. All right, so let me make a superposition of these two states. I have R1, R2 plus L1, L2. Okay, that's a superposition. And of course, why just plus? I could have a minus here too. And then I want to normalize these the states. So, I will put in a 1 over root 2 normalization factor. Okay. Um, Now, so this is the general state of the two photon system. Okay. So the general state phi of the two photon system. I've written it down. Um, Very soon we'll be talking about detecting this two photon system, and that's where the paradox will lie. All right, so I need to write down what my state is, and I have Done. Okay. Now, let us, now here's, it'll be part of your homework. In your homework, there's like a question that I expect you to spend only 5 minutes on. And it's a fun question. It's actually a striking question. There's no math or physics or anything involved. But then the second part of that question will be the proof of this following statement. Okay. So now this is something you have to just accept, but in your homework, you will get, you'll work out a justification for it. So it turns out that experimentally, it is found that the minus sign here, the minus sign is appropriate. So actually, it turns out that the plus sign is actually not appropriate. Okay. And it has to do with parity. Okay. Parity. And I'm just going to write here that has to do with parity and coordinate inversion. Okay. So this will be a homework problem, homework question. So you'll prove it there. So I'm not going to do it here. I'm just going to accept that the correct um, answer is the minus sign. Okay. Um, all right. And let's maybe label this equation as equation one because I'll need it eventually. All right. So there's my quantum state. And so now you can easily, from this, conclude that what is the probability amplitude. Okay. So the probability. So now you want to make a measurement on the state. And then what is the probability amplitude for finding the system with both photons, uh, let's do RCP. Both photons are right circularly polarized. Well, how would you find that? Well, all you have to do is project um, phi, right, onto the state R1, R2, all right? And so that would be um, R1, R2, right? So both photons are RCP, and then we'll also work out LCP. Okay, so if I do a measurement, and what's the probability amplitude for finding both the photons right circularly polarized? Well, I project phi onto R1, R2, and here's phi, right? And so you find if you oops, what did I do here? Um, Come on, just left myself no space. So R1, R2 minus L1, L2. Okay. And so this becomes, as you can see, 1 over R squared root 2, R1, R2, R1, R2 minus like that, right? And so this is 1 over square root 2, 1 minus 0, right? Why 0? Because maybe in the aside here, I should have also said that you can easily verify, right? That um, you can easily verify that the polarization vectors here. Um, uh, so you can verify that x plus iy is orthogonal to x minus iy. Okay, just take the dot product of the two, and easily you can see that you will get 0. All right. So the two, so the right circularly polarized vector and the left circularly polarized vectors are orthogonal to each other. Okay. Okay, cool. So I get 1 over square root 2. Okay. And of course, the left circularly polarized, so L1, L2, the two photons are left circularly polarized by, okay, is also going to be 1 over square root 2. Um, and so this means that the probability itself, right? So the probability uh, for finding both photons RCP or LCP would just be equal to um, R1, R2, phi absolute value squared, right? And it's the same as L1, L2, phi absolute value squared, and it's just half. So you will, with equal probability, find the photons to be, both photons to be right circularly polarized or left circularly polarized. And one thing that you can easily see from here, so one thing that you can uh, one last thing that you can conclude from this is that the probability note, so I'll just say note, the probability of finding one photon, well, photons of opposite polarization, that means that you would have photon 1 right circularly polarized, photon 2 left circularly polarized. Um, and then, of course, you have to project that onto phi, right? And you can see that that's 0, right? I mean, if you were to calculate this sort of probability amplitude, where it's R1, L2 instead of R1, R2, well, that's going to be 0. And of course, it's the same for, L1, R2. Okay. All right. So what's the conclusion from this? So the conclusion here, and we haven't approached the paradox yet. I mean, all this is what you would expect classically also. All right. So conclusion is that if using a circular polarizer analyzer, right? Okay, so the experiment that we're doing here is we use a circular polarizer analyzer to analyze the photons coming out. And so maybe watch this space that I had said earlier. So now let's say that you have a gamma 1 coming out here, a gamma 2 coming out there. And let me put uh, a polarizer that detects, let's say, right circular polarization, Okay, so that's a right circular polarizer. Okay, then what I would find is that if I detect gamma 2 to be right circularly polarized, then I will definitely also detect gamma 1 to be right circularly polarized. So it's 100% with 100% certainty, I can say that if I detect gamma 1 to be right circularly polarized, then also gamma 2 would be right circularly polarized. On the other hand, right, that's what I just concluded, right? This statement down here. All right. Now, on the other hand, if this were a left circular polarizer, right? So then the arrow would be like this. And this is a left circular polarizer also. I don't need that. Then again, if one is left circularly polarized, then definitely the other one is left circularly polarized. That's what we did here, right? That's what we found here. From this calculation and this calculation. The probability for finding so and I'm going to write that down, right? If using a circular well, and the other thing, let me just go back here. The other thing is that if I try to the analyzer that I'm using, if I'm using a left circular polarizer on gamma 2 and a right circular polarizer on gamma 1, right? Or the reverse, that if I'm using circular polarizer analyzers of opposite polarization, meaning if I'm using right circular polarizer on gamma 2, right, and left circular polarizer on gamma 1, then the probability for those is 0%, right? That's what I just found out. And if both are left circularly polarized, then again, 100%. Okay. So that's the situation and let me put that in words down here. So watch this space, this guy is a asterisk, and it goes with what I'm writing down here for the conclusion. Okay. So let me put in words what I was just depicting up there. That if using a circular polarizer analyzer, like I just showed up there, it's an actual optics piece, that I can use. So if using that kind of circular polarizer analyzer, we detect photon 1 to be right circularly polarized, then we can predict with certainty that photon 2 will also be RCP. Okay? And the same is true for LCP, for left circularly polarized photons. Okay? Um, and also we can predict that if we detect photon 1 to be RCP, we can predict with certainty that photon 2 will not be LCP. All right? And so that's how, well, those are the same alternative framings of the same statement. And this is the same. So we haven't, like, I mean, we've couched it in quantum mechanics terms, but this is the same as what classical physics would predict. All you need is some knowledge of circular polarizations. Okay. And from E and M, you would get exactly the same prediction. Uh, so, but Mr. Einstein is involved, so you know that this is not going to be the only story. And sure enough, what Einstein then brought to the so this is where Einstein comes in. And he said that, he was famous for his thought experiments, right? So his Gedanken experiments. So he said, well, this analyzer, the analyzer that is being used, that is something that the experimenter chooses. Okay, so Einstein comes in now, and he goes, the polarizer analyzers that we are using are, the experimenter's choice. So what if I replace, okay, so what if and it's a thought experiment, so even the theorists can do them. So now what if I replace the circular polarizer analyzers, okay, so the CP analyzers on both sides by linear polarizer analyzers. Okay, so now what we're doing is we have gamma 1, gamma 2, and this time the analyzer that I'm using is X polarized. So, I mean, just to be consistent with our diagram, so X you see is coming out of the page. So let's just do the same. So the X polarizer is here, like that, right? So that's X, and on the other side also X. Okay. And so I've replaced the circular polarizer analyzers by linear polarizer analyzers. And now, what do I expect? Well, as you can see from the circular, here's the right circular polarizer, right? That's the polarization. And you can see that there are equal amounts X and Y, right? So let me just write it down here. So CP has equal amounts of X and Y polarization. Okay, so whether you're right or left with a plus or minus in there, right there, you can see that you have equal amounts of X and Y. So it stands to reason, like any person would say that, look, if I have X here, then and you have this, let's say, circular polarized, if these photons are circular polarized, gamma 1 and gamma 2, right? So gamma 1, gamma 2 are circularly polarized. So I would get 50%, like half the time I would detect X polarized photon here, and half the time I would detect a Y polarized photon. All right. And that has nothing to do, like on the other side too. Like, I mean, I stick in my X polarizer and I expect 50% X, 50% Y. Okay. And so it stands to reason that, classically, so let me just write down a conclusion here. Classically, this is Einstein speaking now. All right. That, the pi naught meson decays, and the two photons gamma 1, gamma 2 have separated. So there's distance between them, right? So this is where that spooky action at a distance will come in. The two photons have separated, long before. They're way apart. Like, you could make this distance between the two photons, the distance between the two polarizers here, as long as you like. have separated long before photon one reaches, the photons reach the polarizers. Photon one or two reach their polarizers. So, like, they say that the two photons could be light years apart. I mean, I don't care how far apart they are. So long before photon one or two reach their polarizers. Okay. Now, if the two photons are circularly polarized, then so if the two photons are circularly polarized, then as I was saying up there, then either linear polarization is equally probable, right? Either linear polarization, I mean X or Y, is equally probable. So it's equally probable. So whether I sling in two X polarized polarizers here, or I put in one X, one Y, right? It should hardly affect the results. I should get 50% X, 50% Y on both sides. So the way to write that is that if the two photons are circularly polarized, then either linear polarization, X or Y, is equally probable. And what we do to photon one should not affect photon two. Should not affect photon 2. I had just about enough space. Now, this is what action at a, because you don't want action at a distance. Action at a distance is very counterintuitive. Action at a distance is implying that, this is the classically what you would expect, where you don't have action at a distance, meaning the photons have separated from each other, the two photons have separated from each other, and now I stick in a, they're separated by, like we say, light years, all right, or many, many meters or kilometers, whatever. And then I stick in a polarizer here, X polarized, and I find that, I detect, so therefore, when I then detect a photon, it's going to be X polarized, right? Because the Y polarized photon would be rejected. And but that has nothing to do with what my friend might be doing on the other side. That what So let's say I stick in a polarizer that is X polarized, and he sticks in a polarizer that is Y polarized. Well, we both may. I would expect that, I would get a detection on this side, and he would get a detection on the other side too. Uh, and it seems to me not at all relevant what polarization I used over here. I could have used a X polarizer or a Y polarizer, and I would have equally probable chance of detecting a photon, just as he would, right? So I don't expect any correlation between my detections and his detections, because the circular polarized photons are made up of equal amounts X and Y, and it's 50%, 50% chance that he or I would detect X or Y. Okay. Now, Einstein said this is what you would expect. But then he showed that a quantum mechanical calculation completely says no, that is not right. That is not what you would see. Instead, you would have spooky action at a distance, where, amazing as this sounds, if I were to detect a X polarized photon, then automatically, right then, I can predict with certainty that my friend on the other side will also detect a X polarized photon. Isn't that totally like mind blowing? Like, even though, the distance between the two photons is so large that even light, I mean, how fast can information transmit from one side to another? The fastest anything transmits is speed of light. But in this case, this is instant. It's instant. The moment I stick in an X-polarized polarizer and I detect an X-polarized photon, I know that on the other side, the other photon is also X-polarized. Um, Instantaneously. The two photons could be light years apart, but yet that's what I know. All right. And if I and so this is the paradox, because this really bothered Einstein, and I will um, but first let me prove that to you, because that's the whole Einstein argument. All right. So what Einstein did, so now we're talking quantum mechanics, and so at this stage here, Einstein, with his understanding of quantum mechanics, and his understanding is the correct understanding, no doubt. Uh, Einstein and quantum mechanics. He said that, look, all I'm doing is, let me do the same quantum mechanical calculation, but now in a change of basis. All right. So it's a change of basis. So repeat quantum mechanical calculation above, where we were projecting the state phi onto the state that we wanted to detect. So we repeat that quantum mechanical calculation above, but with a change of basis. Okay, so now and that's a unitary transformation type deal, and so now I'm going to say that the right circularly polarized is, I can write it as a 1 over root 2 x plus iy. Okay. And I proved this to you classically, like I'm just extending the classical method here. So right circularly, you see, so all I'm saying is the x plus iy goes with, didn't I write this out up there? Yeah, right circularly polarized goes with x plus iy, left circularly polarized with x minus iy, right? So that's all I'm doing. I'm writing them as a state now. Okay, so the right circular polarization state, it can be written as this, and the left circular polarization state can be written as this. Okay, and the states x is perpendicular to y, the vectors, right? So what this means is that x1 is perpendicular to y1, orthogonal, right? And x2 is perpendicular to y2. Okay, so that's what these are. So if that's the general enunciation for right and left, then I can now write, and it's a very, very simple calculation. I'm just calculating the same things I did before, but in a changed basis. So this is going to be, now remember, you had 1 over square root 2 r1 r2, right? Minus L1 L2. That's the state that we said state phi is. Okay. But now I'm going to write this in the XY basis. And we'll see where this action at a distance comes from. So what is R1 R2? We can do that calculation. All right. And since this lecture is becoming kind of long, maybe I'll set this as a homework problem. I want you to show, okay? So all you have to do is replace the R1 and R2 by, so, for example, let me just write out a little bit and then I'm going to ask you to show this. So R1, R2 is just going to be, um, here's R1, right? R1 is X1 plus IY1, like that, right? And R2 is then just the multiplication of this R1 by R2, right? And so R2 is another one by square root 2, so squared, and then X2 plus IY2, like that, right? So you can then simplify this, okay? And you can see this becomes a half, and then the x1, x2, you can write that like this, right? The right, this is just x1, x2. All right, like that, and then a minus y1, y2, right? And then you have the cross terms, right? So write them out. So this is where I'll just assign this as homework, cross terms, right? And similarly, L1, L2, okay, is going to be some stuff, right? And okay, and so what then you will find, so homework, prove that state phi is going to work out to uh, I over um, square root 2 y1 x2 plus x1 y2. Okay, a truly remarkable result, because um, what this shows is, so if I were to ask that, what this is telling me is that if I were to ask that, the state phi, what is the probability amplitude of me detecting the first photon, photon 1 as X polarized and photon 2 as Y polarized, okay, then I would just project um, X1, Y2 onto Y1, onto this state, right? And I would find that, the first one, right? So this here is 1, and this, remember, I wrote out these rules up here. So this here is going to be 0, because the overlap between x1 and y1 is 0, right? And overlap between x2 and y2 is 0. Okay, so this that's interesting, and I would also find, so what it's telling me is that if I detect photon one as X and photon two as Y, right? I mean, what's the probability amplitude for that? Well, I'm sorry, what it's saying is that if I detect photon one as X, then with certainty I can predict that photon 2 would be y. Okay. Also, I can, you can, well, also, I mean, it's so, I can't set a homework because it's just so easy. I mean, if I were to calculate this, right, I would find that, so, well, okay, I'm gonna set this in homework. You can prove it trivially that this probability would work, amplitude would work out to be 0, as would this probability amplitude. So there's a remarkable conclusion that we get from this. Absolutely mind-blowing conclusion that if we detect using a linear polarizer, I mean, if we detect using a linear polarizer analyzer, like we were talking about here, remember in this setup, here's your linear polarizer analyzer. So if we detect using a linear polarizer analyzer uh, that photon 1 is polarized along the x-axis, then we can predict with certainty okay, just by looking at this thing here that we calculated, we can predict with certainty that photon 2 will be polarized not along the x-axis, okay, but along the y-axis, polarized along the y-axis. Similarly, if photon 1 was polarized, if we detect it to be polarized along the y-axis, then we can predict with certainty that photon 2 will be polarized along the x-axis. A remarkable conclusion, because this is the part that really bothered Einstein. So he um, so so I guess let me, because these are important philosophical questions, so let me state in writing what I'm trying to say here. So now quantum mechanically, like from the point of view of quantum mechanics, so quantum mechanically, okay, um, there is, so actually let me first state the EPR paradox, okay. I think it's better to first state the correct statement, because there is actually quantum mechanically no paradox. Why? Because the two photons, remember, uh, they form a single system. This is a crucial point. Form a single system, which we designate by, uh, the described by phi, that state vector. And we know that any measurement, this is uh, a postulate, a basic postulate of quantum mechanics, which maybe I'll emphasize more in class, but I think everyone understands that any measurement of this single state phi, any measurement of phi, will yield one of its eigenvalues. one of the eigenvalues. Now, what do we mean by that? Any measurement of this state phi will yield one of the eigenvalues of the measurement operator, right? And who's the measurement operator here? Of the measuring device. I mean, it's a different operation, like of the measuring, um, let me just say that here, operator or device. And what do I mean by that? It matters if your measuring operator is a, a linear polarizer analyzer or a circular polarizer analyzer. Okay. So the point here is that if the measurement device, if the measuring device or operator is a circular polarizer analyzer, the eigenstates are, for phi, we work this out, are R1, R2, or L1, L2, right? Both the photons are right circularly polarized, or both the photons are left circularly polarized. Um, if the measuring device is a linear polarizer analyzer, the eigenstates are, we just worked it out here, x1, y2, or of course you could flip it, x2, y1, right? That's what we were saying here in the conclusion. So the eigenstates are x1, y2, or y1, x2. Okay, so any measurement will yield only one of these possibilities, and this here is confirmed by experiment. People have done these experiments with using linear polarizers or circular polarizer analyzers, and they've found this to be true. Now, this really bothered Einstein because you can easily imagine, um, his this really bothered him because it's like, how does photon 2 know? You know, how does photon 2, like, let's go back to this measurement. So in here, in this measurement here, you know, how does photon 2 know? How does this guy know what kind of polarizer I snuck in over here? How does it know that, oh, you put an X polarizer there and you just detected an X polarized photon, and therefore I must also be X polarized? How did it, how did gamma 2 know that, right? And that's the action at a distance that's going on, that it knows somehow. All right. So this thing here, this uh, really bothered Einstein, and it should bother us also. So here's the paradox. This is the statement of the paradox. So let me actually say this. EPR paradox. that how can photon 2 know what type of analyzer, polarization analyzer, photon 1 will encounter. Because remember, they're separated by light years in principle, will encounter. And then it knows what type of analyzer photon 1 encounters, and then adjust its own polarization accordingly. That's the EPR paradox. All right. But that's what we're seeing here now. And the reason it's a paradox is because we are trying to use these classical arguments, like I said here, classically, that we're thinking that, the two photons, gamma 1, gamma 2, are sort of independent of each other. And they're each made up of 50% X, 50% Y. And we're thinking of them as two separate entities, but quantum mechanically, we know that they are one system, right? They are a single system designated by phi. And so they are correlated with each other. They're always one system. And if you detect one of them to be an X, then the other one has to be a Y. Okay? That we found from our quantum mechanical calculations. Okay, I mean, this is a fascinating sort of conclusion, fascinating calculation, so trivial, so easy. You'll see that it's just a homework problem now in this day and age. All right. But anyway, it's been a long lecture. Thank you for listening. I think that this was a EPR paradox is one of the outstanding philosophical achievements of humankind, which describes the very nature of reality. All right. Okay. Um, More next. I'll see you on Thursday.